Hi everyone, welcome to Math Spellbook. I'm your host Peter, and basically we're going to continue on with our little proof journey that we were on just yesterday. Hopefully you guys are doing well today. It is Tuesday, so basically you made it past Monday, so give yourselves a round of applause for that. Now you're basically almost close to the middle of the week, so let's get through today as well as let's learn some things new. Okay. Hey, Sascha, how's it going? What's the best part of your day so far, my friend? Anyway, oops, didn't mean to have the study timer taken away over there. Anyway, let's just get into the proofs. Time is, we can't waste time. We gotta get through all of time and space here. It's just studying away here. So, let's just get right into it. So I think the last problem we were on was... I did try 9 last night, but then there was so much more details in 9 that I missed. Like when I didn't do it on stream, I wrote it in my notebook. Apparently, since it's because it's 4a, you would have to reduce it to make it even. So basically you would get to... you would reduce it to 2 times 2a, obviously, and then you would have to change 2a to another variable, which makes it just a specific even number. I mean, I could show you the answer, but I don't think I need to do that. Anyway, let's try number 10. Yeah, I think I was on 10. I actually was writing this morning, but it looked pretty interesting, so I thought I would just try it out. Do you want to do a bunch of problems before doing the fundamental theorem of arithmetic? Yes, definitely. So I'm good with the proofs involving odd and even numbers, but when it comes to dividing, when it comes to the divisors and multiple problems, those are the ones I have the most trouble with, so I feel like I actually have to practice these. So, integers. Okay, hit me up on Discord whenever you're ready. Sure. After that, we have I think we can do these 2 problems and then we can go into the fundamental theorem of arithmetic, Sascha. So we'll basically do 10 and 11, and I think we'll then try to get into the theorem of arithmetic, if that's alright with you. Okay, so proof. Suppose a and b are integers. So somehow we have to turn this part into this part. question is that how do we do that? Because we have something that's very, very complicated up here, and now we have something that's somewhat similar but yet somewhat complicated down here. So now what we have to do is like turn this part into this part in some tricky but clever way. Or like show that they're kind of equivalent in some ways. Because the last time we actually had something that was something that looked much more complicated turning into something simple. So this time we actually have something that looks simple, but then it turned into something more complicated. Does that mean we have to think that X is something? Do we have to project that X turns into like something involving B? Because we have B squared minus B, no, B cubed minus B squared plus 5B. Unless we have to transform A is a variable of B and B. Let's see if there's like any certain things that we have to learn about divisor problems, just in case. Okay, these are the odd ones. Let's see, our first step is to apply, so we almost have to bridge the gap, the line immediately, so means that we wrote that for the supposed part. I guess this is the one of the problems where it's like it becomes challengingly harder. Like, you know, when you're given like the first amount of problems, they're like perfect examples of the example you saw in the beginning of the textbook, and then like you're given a problem that seems like it's kind of out left field, and it's like you have to remember like a certain trick or something to actually like understand, or maybe like a certain part of an idea that you probably haven't touched upon in a while. I mean, can we turn the X into like something involving B or something? Because I mean, yeah, I don't know how to start this one. If anyone in chat has any suggestions, feel free to give me a hint if you think it will help me at this point. What's the next? Actually, I'll write down the next problem. If I have to write more, I'll probably move to the side. So suppose A, B, C, D are part of the integers if A and C then proof in this one. B is equivalent to A. Put AX and D is equivalent to CY with C Y element of the integers. These two problems are pretty difficult. I'm trying to think like how to manage these two. Like 45 minus... So we've been on this for like 18 minutes. I'll wait 2 more minutes and then I'll probably look at the solution. Because I think the best way to like basically know when you're really stuck on a problem and when you know when to look at the answer is like when it's like actually like been over 20 minutes. Do I have to do like some mathematical gymnastics to make it look like this? Like, do I have to turn X into like B or something in order to, or something involving B? It's been like 20 minutes, so hold on. Wait, what am I thinking? I like that emote. I like that emote, Sascha. Oh yeah. So I can't show the answer in front of you guys because it's from an app I'm using. So Guess I'm gonna have to write it down. Book of proof. Where is it? There we go. Direct proofs, number 10. Okay, so I'll move this to the side, because according to them, it's like assume A and B, then there exists an X within. Actually, I've never seen this symbol before. I've never seen that backwards E before. Or, well, not really E, but you guys get what I mean, because I'm so used to seeing this one, but I've never seen this one backwards. I wonder what that means. Thus... Means the same thing. Oh, okay. Like Tech Discord bot is trolling us hard on April 1st. What do you mean by that? What do you mean by that, Sascha? It means the same thing? Oh, okay. Let's look at what this proof means. Okay, so assume that A is a divisor of B, then there exists a X is an element of the integers, and is an element of. But why would they write it backwards? Like that's the one thing I'm not understanding. Well, they replace arrow by something else. Oh, okay. Just silly notation. Oh, okay. So should it be like this E then? Well, I shouldn't call it an E. Like that's an epsilon, I think. So it doesn't matter if it's like backwards or like this way, like the way that I'm used to. Let's see, there exists an X, which is an element of the integers, which is also an element of B equaling X, which A, thus squared. So. Oh. Okay, so they want you to use the property of like B as sort of like a thing that tells you that A will still divide into that. So no, this way would be that z, the integer, is an element of b. Oh, okay. So why is it backwards? That's the one thing I don't get. Like, what does it mean when it's backwards? But we want b to be an element of the integers. So is it written backwards like that because you also want to include b in that notation? Because obviously you don't want to write like b equals like, you know, x times a, right? It's just another way of basically just putting all those ideas into one, I guess, statement, right? Is that the reason why they wrote the e like, I mean the epsilon like that? Okay, that's a fairly interesting proof, actually. Because I thought, like, when we did this proof, when we were trying to do this proof, I thought you had to turn this into this. I didn't think about, like, just basically just squaring everything and just putting them all together. Because I thought that would be a totally different number at that point. Alright, so what is... So a times c. So if we have that, then it would be a times c, which would then be equivalent to ax times cy. And if you, well, actually I should have wrote it like this: a c bd. And then you can do this where you just so BD is equal to AX times CY, which is equivalent to AC times XY. Therefore, AC I mean, that looks kind of too simple. At the same time, I feel as if, like, I'm probably just... I feel like that's not right. But at the same time, like, it feels like it logically makes sense. Maybe the solution is a lot more involved. We'll see. It's number 11, chapter 4. So... chapter 4. Where are you? Here we go. Chapter 4 exercise. Number 11. This is... Here it is. So suppose... Yeah, we already clarified that they're integers. Okay. We wrote that. Yep. Now since it multiplies... And other than by... Oh, okay. Oh yeah, we forgot to write that part. Okay, so it's not exactly the way they wrote it, but it feels as if we got the proof correct. I mean, I felt like it felt too simple, but at the same time it just... Now, obviously it's not simple. I say that because I felt like I just got the answer too easily, and I felt like this can't be right because I got it too easily. But it does look like we did have the parameters of the proof kind of correct, I think. I mean, for all those that are like higher in levels of math, like, you can judge me on that. You can basically say, yeah, it doesn't look elegant. It looks kind of, I mean, it looks like probably like too simplified or something. Or maybe like, you know, like, hey bro, like the simplest proofs are usually the easiest ones. So, you know, I don't know. I felt like I got that one too easily. I felt like I didn't struggle enough for that one, actually. But then again, I did look at it and I felt kind of intimidated by it. Maybe I intimidated myself based on that. But the one before that one was kind of like, wow. I was like, that is different than what I would think. Cause this part I felt as if was kind of like, oh, so you have to clarify there exists an X where it's like this. I mean, when I repeat it to myself, I think it does make sense, but at the same time I'm like, do I truly understand this concept? Like the concept of why there exists an X in the integers, which B is also an integer that X times A equals B. If I'm stating that wrong, like, let me know. But yeah, maybe like maybe sometime, like, if I like just put these problems down and then I try to pick it up again, maybe I'll end up recalling this part, recalling this whole proof right here. But who knows, because like the more I do these proofs, like I think when it came to like proof writing, when I first started doing proofs involving even numbers, like even integers, they were pretty simple. They were actually kind of easy for me to grasp onto. But when it came down to like division based proofs, those were kind of like, I think they were like a new experience. Will I remember how to do them all? Like, probably not. I probably have to do more of them. So, where is it? Oh, that's more proofs. No, that's not what we want. We want direct proof here. So I'll just scroll down here, back to the questions that we were on. Here we go. All right. I think we're ready. Let's see, how much time do we have left? Okay, I think we have enough time to do the fundamental theorem of arithmetic. So I don't know if Sascha is still in the chat, but let me see here. I'll just go on Discord on the stream VC. Sascha, I just sent you a message on Discord, like, if there's anything you need me to do to help you set up. Because I think Sascha really wants to explain the fundamental theorem of arithmetic with us. Hey Jeff Gross, what's the best part of your day so far? I mean, it is April Fool's Day, so I guess it's a day to be silly, I guess. Okay. Alright, Sascha, you're on stream with us.
Hi. Can you hear me?
Yeah, I can hear you. So chat, let me know if you can hear Sascha. He's an awesome mathematician and he's doing research in, so actually, tell us about your research a little bit. Like, how's the process on that?
Slow and painful, but sometimes fun.
We can, oh, you can hear Sascha? Okay, cool. Okay, Sascha, do you need me to set up anything?
I think we should go on something that we can both write on. So maybe
Okay.
an Excel draw or a tail draw.
Okay, the same software, I mean the same browser, like write-on software you showed me last time, right?
Actually, I want to try maybe another one because I've seen people use another one that seems a little bit better. So maybe
Okay.
we will get less lag because last time we were getting. How do I invite someone?
Is it still on the
Can I?
browser?
Yeah, it's called a TL draw or something.
Okay, can you send me the link and I'll just basically
se-
bring my browser down?
Yeah, but I don't know how we share links, like to be in the same session.
Let me see. I don't know. I have to make an account with this thing.
Yeah, I'm not really done for that. Okay, maybe we can just go back to Excalibur then. Excalibur.
Well, actually, I'll save it in my favorites just in case. Like, you know, like maybe next time we could probably try test it out.
Yeah.
So actually, while we're setting up, Sascha, why don't you explain your research? I'm pretty sure
my
it's
research?
amazing. Yeah, I'm pretty sure it's amazing stuff that people will probably like comment on.
So my research is on Hodge theory, which is a field of algebraic geometry. I mean, it's pretty much a topic when you want to study topology of complex manifold, projective variety, stuff like that.
Oh, okay.
Okay, I send you
A link?
a link, yeah.
Okay. I'll just open it.
So there is a lot of famous problem in Hodge theory. For example, there is a famous Hodge conjecture, which is one of the Millennium Prize.
Oh, okay. Alright, so here, this is what me and Sascha worked on last time, I believe. Oh, no, this is
I think it's empty. Should be empty.
Oh, no, this is what Mavort was trying to teach me. The what is it? The distance between planes and lines.
Okay, I see. Yeah, I remember that too. Yeah.
Yes, so we'll just drag it down here. So yeah, I don't know if I can share with you, unless you have the particular was it Xcal draw that you can link it to me.
I think they're linked now. No?
Are they linked? So like, can you write on this one?
Well, I'll send you a link on Discord.
Yeah, because like I think I clicked it, unless I have to refresh my thing.
Do you see
here we go. I guess like the weird thing is that like, you know, when it shows like the picture, I clicked on the picture link instead of the link above it.
Oh, I see.
So I think it was like two different links. Okay, so all right, so Sascha is actually going to introduce us to the fundamental theorem of arithmetic.
All right, so let's first start with a statement, and then after that we're gonna try to explain what the words mean in the theorem. So, theorem.
Yeah.
Fundamental.
So the reason why we're kind of going over this, guys, is because like last stream, like yesterday, Sascha basically said like, oh, the divisor / multiple like proofs that I was doing, if I knew how to do that, then I would be able to understand the fundamental theorem of arithmetic. So that's why we're kind of going over it a little bit. Yeah, like the divisor proofs are like kind of like tricky for me.
Yeah, so hopefully you will get a little bit better when we go through this proof.
Okay.
Because there are a lot of argument about that, so you will probably, hopefully you will gain some intuition and a little bit of knowledge about how we write proof.
Yeah, that's when when you guys talk in chat, I feel as if like you guys are speaking out of your intuition, and I'm like, I don't think I'm there yet.
Yeah. I mean, to be able to write the proof, you at least need to understand why it's true, right?
Yeah, at least I know how to do proofs involving even and odd integers.
Yeah, I mean that's already that's already a good start. So
okay.
You're not that far.
Yeah, please continue. Sorry.
Okay. So do you know a little bit about what the theorem say? The fundamental theorem of arithmetic.
I believe the fundamental theorem of arithmetic says that whenever you break down numbers, you can always break them down to a unique set of prime numbers.
Yeah. Yeah. So I think last stream you mentioned they were kind of the atom for a natural number.
Yeah, that's what I thought was cool about the fundamental theorem of arithmetic.
So that's pretty much the whole idea. So let n be some natural number, and we're gonna assume that n is bigger or equal to 2.
Okay.
Then n has a unique factorism into Prime's number.
Mm-hmm.
So they will be written something like that. Where pi a and pi j are different primes number. And there's also another aspect to this theorem. This decomposition is unique.
Okay. Like, can I ask a question?
Yeah.
So in math, what is defined as uniqueness?
So that's a really good question. So usually when we mean unique, it almost never mean unique. In that case, what unique means, it means that the primes are completely determined by n, and this decomposition is unique up to rearranging the order of the primes.
Okay.
Up to the order of the primes. So maybe we can just go about like some numerical just computation to see how it would work. So maybe we can take some numbers. So maybe we can start with 144.
Right.
And I mean, usually, I don't know if you have ever done that, but usually when we want to find the prime factorization, what we do is we break down this number into a factor.
Yeah.
So probably 144 is easy to write as 12
times 12.
Yeah. And after that, we can break down those factors into a smaller factor until we reach the primes.
Right.
So here, maybe 12 will be 3. Maybe we can go another step.
Yeah.
And the 4 now can be broken down as 2s.
2s, yeah.
And now if we just, if we pack common factor together,
Like,
we get that.
Right.
And this gives us the prime factorization of 144. Of course, we can change the order, so we could write something like that. That would count as the same prime decomposition.
Right. So basically, the unique part is basically saying it doesn't matter how many times you break the parts into different ways. It will always be that configuration.
Yeah, exactly. So if we go back to the theorem, you see we have the pi throughout the primes, and then we get some exponent. Well, no matter what prime decomposition you find for n, you will always find the same prime numbers and the same exponent.
Okay. So I'm guessing, like, this is my way of summarizing. It's like when it says unique, it basically means that no matter which way you do it, no matter what different numbers you use, it will always go back to those basic building blocks. That would be the same. Okay. Yeah, so the exponent and the primes are unique, and the only thing you can really change is the order. So does the definition of uniqueness only apply to, I guess, this would be like in number theory, right? Or would this be like just arithmetic?
I mean, we usually use uniqueness in mathematics, and I mean, as I said before, it's really rare that unique really mean unique. It usually means unique up to something.
Yeah, so like I'm going to break down my question like a little bit better. The term uniqueness, is it different within different branches, or is it encompassing all of mathematics, that this definition of uniqueness that we've just said is what it means to be unique in all of mathematics?
Yeah, so
Go on.
Yeah, I mean, usually you have some context. So unique here mean, as I said, the pi and the exponent are completely determined by n. But other than that, that's what unique mean. I mean, that's kind of funny because when we go through the theorem, the fundamental theorem of arithmetic, we have to prove a bunch of preliminary results, and you will see other theorem that have uniqueness properties inside of it.
Okay, so uniqueness is basically like just no matter what system or I guess style you use or numbers you use, it will always turn out to be the same type of end result.
Yeah.
Okay.
So maybe here I can write, maybe if I want to be more precise, the p i's and n i's are determined by n.
Okay. So yeah, I think we can continue on.
Okay. So there is like kind of two parts of this theorem. There is one part which is not too bad, which is existence. So we have to show that for every integer greater than 2, we can write it as a product of primes. And then there is the harder part, which is to show that actually this decomposition is unique.
Okay.
So we kind of have to break down this proof as a two-step process.
All right.
Okay. So before we start with uniqueness, not uniqueness, but existence, which is the easiest part, we first need some tool from arithmetics, which is proof by induction.
Okay, yeah, I'm familiar with that one.
So you're familiar with that one? Okay. So maybe we can just do a very simple example just to make sure we're on the same wave, okay?
Okay.
So let's say just as an easy exercise, we're gonna prove like probably the most famous proof by induction. I mean, you probably heard of that, but this is like one of the you know about the great mathematician Friedrich Gauss.
Yes.
When he was like in I think elementary school or something, a teacher was kind of bored and asked the student to add up the number from 1 to 100.
Yes, I'm familiar with the story.
Yeah, you're familiar with that story, so we're gonna go with with the proof of that.
I already immediately knew what you were talking about at that point.
I mean, that's kind of like the first example that people.
And actually, that's kind of funny because not many math classes actually teach that story, and I think that they should.
Yeah. So we're gonna do this proof by induction, okay? So maybe I can just write the structure of the proofs, and then you can fill up the details. So we want to do an induction on K.
Okay.
So we have to deal with the first case, which is case
1, which is basically when K is equal to 1.
Yeah. Here I'm a little bit sloppy. I should have clarified that this is for all n greater than 1. Obviously, I want the n to be some integers. Okay. Okay, so can you do the case k equal 1 for me? I mean, n equal 1. Sorry.
Yeah. So let me see. How do I activate my pen here? Wait, can I just write? Oh no, I can only. How can I activate the pen here? I remember I did this before. I just don't remember how the controls work. Oh, here we go. The controls are up here. So case 1, basically n is also like n is 1. So basically we would have. Oh, that's too thick. So erase that. And then we'll do the pen here. So it'd be 1 times 1 plus, and that would leave us with 1 times 2. Right, like I feel like I was going crazy for a second. Alright, so that's case 1.
So just to be sure, because I think we just to be sure, so this is an evaluation of the right side, right?
Mm-hmm.
And then you sort of explicitly evaluate the left side, like.
Yeah, I'll write it. I didn't like the way I wrote that sigma. Okay. is equal to 1, k, and then goes to n. Okay.
Yeah. So here we can probably replace the n by the actual value. So.
Oh, 1.
Yeah. And so this sum is obviously 1, right?
Right.
Okay. So now let's do the hypothesis, inductive hypothesis.
Mm-hmm.
So let's assume there exists some k such that, okay, let me not call it k because it's confusing. Let's call it n, such that the theorem holds, right?
Okay.
And now to be able to do the proof by induction, we have to show what?
We have to show that basically, I guess, like, the series that we're talking about is actually equated to, oh, no, we have to show that n plus 1
Yeah, exactly.
equals the same, I guess, the same result in, like, I guess, like, a configurized fashion with n plus 1.
Yeah, so we have to show that the thing we want to prove holds also for n plus 1, knowing the fact that it holds for n.
Yeah. Because I think I remember that one. So basically it would be like n plus 1 times n plus 1 plus 2. And then basically after that you end up with n plus 1, n plus 3 over that. And I mean, you can do FOIL on that one.
Yeah, usually what I would advise people to do is to start with the more complicated side.
Okay.
So here probably the part with the summation is probably the hardest part, right?
Uh-huh.
So let maybe just write the summation part for the case n equal for the case n plus 1, okay?
Okay, so I'll just erase this then.
Yeah.
Because this is also, actually I have to practice series too, so it'll probably be good series practice.
Yeah.
So erase that. Series from n plus 1, right? And then we still leave it at k. So k is equal to 1. So then we're left with n plus 1. Right. So
not quite, right? Because we're not summing n, we're summing over k, right?
Oh yeah, right.
Okay, perfect.
All right.
And now the goal when we have a proof by induction, or at least when we think that the proof by induction would be efficient, is that we're able to somehow make the case n appear in the expression, okay?
Okay.
So here, maybe I can give you a little bit of help. Here, maybe what we want to do is maybe remove the last term of the sum. So we maybe want to remove the case k equal to n plus 1 from the sum.
Okay.
So split the sum into two parts.
Split the sum into two parts?
Yeah.
So what, you mean like this?
Not quite. Okay, maybe I can. Maybe what I said was not very clear. So let me.
I'll erase it.
Maybe give you. Yeah. So what I mean is this sum we can break it down. So we can say, okay, I will throw the last term of the sum.
Mm-hmm.
But if I do that, I have to end my summation to n, right?
Mm-hmm. Oh, that's what you meant. Okay.
Yeah. Sorry, that was not very clear. Okay.
Mm-hmm.
So do you agree that those, I mean, what I wrote on the right is in fact equal to what is on the left?
Yeah, I see that.
Yeah, just usual property of summation.
Mm-hmm.
Okay, and now what is good about this expression? Because recall, if we want to be successful with the proof by induction, we have to be able to relate that to the case equal n.
Mm-hmm.
Well, what is the guy on the right?
So basically, when k is equal to 1, when it goes to n, that basically is that series. But on the left-hand side, it's basically just adding like n plus 1. So the only difference is the n plus 1 part.
Yeah, but I mean, do you agree that the guy on the right is pretty much our inductive hypothesis, right?
Yeah.
So we can use our inductive hypothesis on the guys on the right, right?
Right. Okay.
So let's do that.
Alright. You want me to write it?
Yeah, I want you to write it.
Okay, let me just scroll down. Okay, so it's like n plus 1 plus n plus 1 over 2. And I'm guessing you want me to simplify the whole thing, right?
Yeah. Now you just have to work out a little bit with the algebra to be able to obtain the wanted form, but
Okay. Then we're left with 2 on the bottom. Plus n squared plus n. Scroll down. That leaves us with. Well, actually, I'll write it. I'll write it so all the variables look nice. So n squared plus 3n and plus 2 equals 2.5. Now I'm guessing. Do you want me to factor it out, like the portion?
Because our goal for the case n plus 1, I will write it on the right side, is to have, so what would it be? It would be n plus 1 times n plus 2 over 2. That's what we want to obtain. Yeah. So you basically found it.
Yeah, with simple FOIL, I think it's easy at that point.
Yeah. So you did it. So we proved the inductive steps. So by the principle of induction, we prove it for all n.
And then we would write like therefore, like the series is that.
Usually they would say, okay, we're done with the induction. So we're done with the induction.
And then we'll put like a small cube here.
Yeah. Does all n really equal to 1? The wanted formula hold, and then you can put the box.
Yeah, that's do you use a box when you finish a proof, or do you make a unique signature for yourself?
I put a box.
Oh, okay.
But I mean, I don't usually write it down on the paper, because usually when I write the proof on paper, usually it's a very scratch word. You see?
Yeah. Actually, I want to ask you one question. Is like, what is the difference? Like, how do you know which something is scratch work and which one is actually meant for the proof to make logical sense?
I mean, okay, usually when I write on paper, it's always scratch proof, but I mean, I can still tell if the proof is correct, because the main arguments are true, or I'm convinced about them.
Yeah, because I think when it comes to like scratch work, I'm like, like if I put scratch work, then that means it's not an elegant proof, or my professor's gonna think like, oh, this is not very good proof writing. So I think like when people get into proofs in math, I think they get intimidated by, what is scratch proof and which one is necessary to put on the paper. Like, what questions would you ask yourself to say, okay, this is scratch work, I don't have to put this in the proof, or, oh no, this is not scratch work, this is actually necessary for the proof to make sense. Like,
so there's a few things that would matter. So first of all, if I'm just writing down the proof for the first time for this theorem, I will probably just don't worry too much about it and just wrote everything on a piece of paper, and like just don't bother about if it's scratch work or not, because
everything you write, basically, it's like, as long as it just looks nice, you just basically put it on the paper. It doesn't matter if it's scratch work or just formal proofwriting.
Yeah, but okay, that's the thing. So
Yeah.
the first time I prove it, usually the proof it will be a little bit messy. There may be like some part that are wrong, and I have to to work it out. But
Right.
at least I can get the idea out of my head, like why this theorem should be true, and write down some argument. You see. And and after that, I will usually refine a little bit the proof to at least the main part to be at least true.
Yeah.
And usually when I was an undergrad, what I was doing is after that I will wrote everything on LaTeX.
Okay.
And this was like my formal proof, like
right.
Like the clean version that someone who doesn't necessarily know about the theorem could read it and know about it and agree that this is a valid proof.
Okay.
Unfortunately, over time you sort of develop some bad habits.
Such as?
Well, sometimes there's like some details are like a little bit too painful, a little bit too pedantic to write down, or make like the proof way too long. So usually people skip over them, or at least just wrote like a one sentence argument to explain what's the idea, and then say, oh yeah, it works, but I will not bother to write it down. You see?
Oh, okay. So like sometimes I guess like people would like take away things that I guess considered scratch work, but it kind of would be considered important. But I guess they're writing for higher level like mathematicians. They feel like, oh, I don't need to put it in because this is obvious by looking at it. Oh, okay.
So it kind of depends. When you start, you want to write everything down because usually when you start, you're not very too confident about what makes a proof good and what make a proof
like it wouldn't be helpful for me because I'm so used to seeing every step done, but like I guess for someone that's more experienced in the proof, it's so obvious, like why would you need to put that step in the proof? Like something like that, right? Gotcha. Okay.
Yeah, but sometimes it depends because sometimes when you really like expert doing technical stuff, well, for them everything is sort of easy, and for you it's like everything is sort of hard.
Yeah, it's like basically the teacher, like the mathematics professor or teacher that basically is like they skip a step and then the students raise their hand. It's like, wait, well, how did you get to that step? But then like other people are like, it's so obvious, why do you need to like clarify this extra step here?
Yeah, I remember I had a seminar class about a paper of a seminar class. Usually the evaluation is pretty much like you do a oral presentation about like some paper in the field.
Oh, okay.
And I got like some very famous paper about from Donaldson, which is like one of the top differential geometry of our time.
Yeah.
And there's like at the end of the article there's like some famous counterexample to some famous conjecture. Like there was kind of like for the field it was like kind of a very big moment because a lot of people thought that this conjecture was true, but Donaldson found a counterexample. Okay. But I'm not too much in that field, and I had like other PhD students who were like researching in that field. And when I told them that the teacher gave me that subject, they said, "Oh yeah, I never understood the proof inside of the Donaldson paper. There's like there's too little details to be able to understand."
I don't know whether to feel happy or feel worried about that, because it's like even mathematicians don't understand each other, and I think it's kind of funny. Because students grow up like basically saying to their math teachers, "I don't understand it because you skip so many steps," I guess I'm kind of glad that mathematicians even experience that problem. And there's some mathematicians that are like, "You need to write this extra step here because I don't get it."
Yeah, that was kind of funny because when I did the oral, I was like, okay, Donaldson does not give us a lot of detail to be able to carry the computation, so I had to invent some weird notation. That's not from him, this is my bad if the notation is bad. But at least at the end, everybody
I'm not the only one with that problem.
At least everybody at the end understood how the proof worked and how the computation were done in the proof. But
right.
I mean, the guy is pretty much a field medalist and like a very good mathematician. So I guess for him everything is like sort of easy. And I mean, for us,
like for us mere mortals.
That's another
story. That's pretty good. That's pretty good. Okay, so getting back to topic. So how does the proof of induction help us with our theorem of arithmetic?
So pretty much usually the proof is done using induction. Okay.
Okay.
And so I think the very classical proof is using induction, but for the proof I want to present today, we're gonna use something else. Okay.
All right.
I mean, I don't know if I told you, but I'm teaching like a few classes this semester.
Oh, that's good.
And I'm teaching like a more advanced linear algebra class, and I mean the students are like in second years of undergrad, something like that. Like at this time, it's probably like their third linear algebra class, and every time I have we have to do it by induction. Every student are kind of, oh no, not again. Like usually people does not really like proof by induction. I mean, it's kind of funny when you read a little bit more graduate lectures, like, oh yeah, I mean, I did the base case, but I mean, you can just go by induction and just do the general case, but I will not bother writing down all the steps for the hypothesis induction.
Right.
So it's kind of funny. So there's actually an equivalent reformulation of the principle of induction, the natural number.
Okay.
So maybe I can just write what is the principle of induction, like very formally. So let's say P is a proposition that depends on some natural number.
Okay.
On n, which is a natural number. So, for example, if we want something very concrete, we could take, for example, the previous problem. So, in our previous problems, Pn could be, our proposition could be could be that for a natural number n, this equality holds. Okay.
Okay.
And you see that the propositions sort of depend on what n we're choosing, right?
What's so is that supposed to be a 2 underneath? Like n?
Oh yeah, a very bad 2.
No, I'll write it. I can write it.
I don't know what Yeah, sorry about that.
No, it's okay. No, it's okay.
And what's the principle of induction tell us? It say, okay, if you know that for the proposition is true for some number, let's say Pn0, so n0 is a natural number, and you also know that for all n in the natural, we don't have to. It doesn't have to be for all natural number. It can be for all n better than n0, but of course we want n to be a natural number. You know that you have this implication. You know that the case Pn implies the case Pn plus 1. Okay.
Okay, so for all n that is greater or equal to n not n is an element of the natural numbers, or Pn implies, or is that equal to?
No, it implies.
Implies, okay. Because I didn't see the little arrowhead at the end.
Oh, there is no arrow? Okay, maybe it didn't render right.
No, I know. I meant that I just didn't see it pointing. That's me. It's not you. Don't worry. You're
okay.
So when we talk about the implies part, right? Implies that Pn implies Pn plus 1. So does that mean that the properties of Pn automatically go to the next part in the series? Like
exactly. So if the property holds for Pn, it also has to hold for Pn plus 1.
Okay.
So what is on the right side is precisely the inductive part.
Okay. Actually, like, after you explain, like, the fundamental theorem of arithmetic, there's another question I want to ask you, but I'll wait until the end.
And so what we have on the left is the base case.
Mm-hmm.
And on the right side is exactly the inductive hypothesis. If we go back to the proof you just wrote, so we pretty much did that because we say let's assume that for some n greater than 1 we have this equality that holds. So so this part is really we're assuming that the theorem is true for some Pn.
Mm-hmm.
And then if we want to show that we have the implication that we wrote on the additive part, we have to show that the case Pn plus 1 also holds.
Okay.
So just to be sure, when we have an implication like that, the way we prove that is we assume the hypothesis. In our case, it would be Pn hold.
Yeah.
And if we want to show that the implication is true, we have to show that the conclusion is also true. So Pn plus 1 is also true.
Through the proof of induction, right?
No, so this has nothing to do with induction. This is just showing a general implication.
Okay, so why did you write induction like proof right here? Like,
but I said this is the inductive part of the proof. Like, so in the inductive part, what we said, okay, the theorem holds for some Pn, and then we show that it also holds for Pn plus 1.
Oh, okay.
So what does the principle of induction tell us? Is say, okay, if we have both this, okay, so we know the base case is true, and we also know that we have this domino effect that if it's true for n, then it's also true for the n plus 1.
Okay.
Then the principle of induction said this is true for all n greater than 0. Of course, n is a natural number.
So it implies that all n is greater than or equal to n naught. N is an element of the natural numbers, thus Pn.
Yeah. So this is what we use. So in our proof, what we did is we showed the base case, and then we showed the inductive part. So we show that if it's all for some n, it has to also hold for n plus 1.
Mm-hmm.
And then the left of what is left in the proof is just applying the principle of induction. So if we have what is in the big if we have what is inside the big parentheses in the top hold, then we should have the conclusion that holds. So the proposition is true for all n.
Because you're basically saying we need the base case, and like basically through the induction part that basically classifies that like Pn is basically going to eventually go to the next number within the sequence. So basically it will continue on forever with that same routine.
Yeah,
and
exactly.
And basically that implies that all the numbers like higher than n naught basically is going to continue on with that same sequence, right?
Yeah. So yeah, exactly. So this is really the domino effect, right?
Right.
Like if you have like a sequence of domino and you push, and you know that if you, I don't know, maybe you have a domino that falls, then the other also have to fall.
Yeah.
So this is like the inductive part, and if you also know that the first domino was pushed and it fell.
Yeah.
Well, you can conclude that all domino must have fallen at some point.
They're all going to follow the same pattern no matter what. That's basically what you're trying to say in a nutshell. Okay, gotcha.
Yeah. So the idea is, in general, we can do that about proposition on natural number.
Okay.
Okay. There's actually an equivalent formulation of that, which is a little bit more useful, but a little bit maybe weirder if you've never seen that.
It'll be something interesting. I will say that for sure. If it's weirder.
So there is an equivalent formulation of that. So when I say equivalent, is that if you have the inductive principle on a natural number, you can conclude the thing I will write. And if you have the thing that I write, you can figure out the inductive principle out of it.
All right.
So this is called the well of the ring of the natural number.
Well of the ring of natural numbers?
Yeah.
And which branch of math do you learn this?
So usually you learn that in arithmetic.
Oh.
But not like, primary school arithmetic, like when you do proof on natural
Proof
number.
arithmetic.
Yeah.
Like, okay.
So what it says, if S is a subset of the natural number, and S is not empty, then S admit a minimum. A minimum. I guess I'm missing an M.
Yeah.
So what I mean by minimum is there exists some M inside of S.
Yeah.
Such that for all little s inside of big S, we have the following bound.
Like it's bounded below?
Yeah.
Okay.
So it's a minimum.
All right.
Yeah.
What's next?
So this is all what the ordering theorem says.
Oh, okay. So let's see. If S is a subset of the natural numbers and S is not empty, this S, this S has a minimum in which there exists an M in the subset of S that all of. So is this a small s? Like all s is an element?
Yeah, all
of s?
small s. Yeah, I should have maybe something else, maybe x. Or
No. It's fine. It's fine. Because I think I've seen that so many times that I'm like, oh, okay, this must be like the elements in S that is not M. So basically, that's what I thought it was. So you're good. It's okay.
Yeah,
So
I mean x could be x could be M.
Yeah.
This will not be a prime because in that case M is.
So basically, M is like the lowest, like the. No, I was gonna say something else, like the lower bound of like the set, right?
Yeah. So I think you did some real analysis a few streams ago, right?
A little bit, yeah. Like.
And you had like some very similar principle.
Yeah, I did learn a little bit about supremum and infinitum.
So in the real number, you have a principle that if you have some bounded set, which is which is not empty.
Yeah.
You can. I mean, I guess it can be empty. If true, but okay. Anyways. I mean, no, it has to be. Non-empty. Okay. Then you can always find an infimum or a supremum, right?
Okay.
You did that a few streams ago, right?
Yeah, I think that's when it was concerning infinitum and supremum. So like supremum, it has to be I have to remember. I think it has to be a least upper bound, and basically I forgot what the the second part of that was.
So this is the infimum is a least upper bound, which is also the greatest. So among all the lower bound, this is like the greatest you can have.
Yeah, and nothing can be smaller than that.
No, something can be smaller, but nothing can be bigger.
Nothing can be bigger.
No. I mean, in that sense, any lower bound has to be smaller than the infimum. And something that was a little bit weird about infimum is that sometimes they're not part of the set, right?
Right.
So, for example, if I write the infimum of I don't know, the semi-open interval like this. So this is the interval that contains 0 to 1 with 1 include but 0 exclude. The infimum will simply be 0. So you can have the infimum not be part of the set, you see.
So wait, is this a closed interval or is this an open closed interval?
Open close. So when I put, I think in English you write something like that instead.
We write like
parentheses and something like that.
Yeah, it's something like this.
So those two things are the same.
Oh, okay.
So what's weird here is that the infimum is not part of the set, right? Because we explicitly.
But it's still considered as the infimum because it's literally like bounded there.
Yeah, but what is different with the minimum is the minimum has to be part of the set. Yeah.
Oh, okay.
So it has to be part of the set.
So the thing that you wrote wouldn't be considered part of this definition, then, is what you're saying? Because it's not. So what you wrote here, this would not be included in.
I mean,
based on the definition. That's what I'm
Yeah, but
saying.
I mean here we have other problem is because if we look at the interval 0, 1, this is real number, and here we're just dealing with natural numbers. So it's not the same thing.
No, I'm just basically saying like if it was like
Oh, yeah.
based on the definition.
Yeah. So I mean this example showed that for example the real number are not well ordered.
Right.
Because for example this set has no minimum, it just have infimum.
Okay. Carry on. Yeah.
Yeah, there's actually a very controversial theorem when back it was released. This is an early theorem about set theory that said that any set,
right,
non-empty set, admit a well-ordering ordering. Mm-hmm. So you see here the ordering is given by the just less than equal, right?
Yes.
And for the real number, we can also use a similar thing, the less than equal, to order the real number, right? Mm-hmm. But the real number are not well ordered because, I mean, at least with the usual, inequality sign because of an example like that, right? Mm-hmm. But the theorem says actually you can find an ordering on the real number such that you have the well ordering property that holds. Okay. This is like a very weird theorem to think about it because it's really not obvious how you should build such ordering on the real number. So it's really it's really weird.
I guess the question I would have to ask is like, what does it mean to be well ordering?
So this is pretty much what I wrote here. So okay, maybe I can write it in general. So let X be a set. I think I want it to be non-empty because I think I can get in trouble. So let's maybe just assume that for be sure. Okay. So you can put some ordering on the X. Mm-hmm. Okay. And basically, I mean, I can write it down formally if you want, but basically you want those following property. Okay. First of all, you want A to be less or equal to A. This is called the reflective. I mean, I don't think it's called reflective. I mean, usually it's for equivalence relation, but whatever. Mm-hmm. You want some transitivity. So if A is less than B and B is less than C, you want A to be less than C.
Let's see.
What else do you want? I mean, usually you want that either A is lower than B or B is less than A. Mm-hmm. And both hold if and only if A is equal to B. Okay, something along those lines, okay?
Do you also have to incorporate, like, say, like the definition of association, communication, what is it? Distributive property, the associative property, and the commutative property within this, or?
So you mean like if I have like some arithmetic operation like addition or something?
Yeah, does that have to be included in this definition?
No, because X can be, X is just a set. It does not have a structure of addition of multiplication.
Okay, so it's not like something like a field or something like that. Okay.
Yeah, I mean, you can usually add those in the definition if you make X to be like something like you say a ring or a field. You can say, oh, I have an order ring. What does it mean? But then it
wouldn't be a set. It would be mainly like a field or like something else.
Yeah, it would be something with more structure.
Okay, gotcha.
So a set can be pretty much anything. Like like I don't know, the thing I have in my pocket from a set.
Okay. So how does the well ordering of natural numbers help us?
So the well ordering would what was the question?
So how does it help us get to the fundamental theorem of arithmetic?
Okay. So maybe I can remove what I was talking about below. So one part which is kind of hard in the fundamental theorem of arithmetic is first to find some prime number.
Okay.
That divides our n. Mm-hmm. Okay. So the first part, which is a little bit hard, is the existence.
Okay.
of some prime. Okay, maybe I can. Okay, part of the existence. Okay, I will. Okay, I will not write example. We're gonna prove a little lemma first. Okay.
Okay.
So let n be some natural number, and assume that n is greater or equal to 2. So we are in the, the hypothesis of the fundamental theorem.
Okay.
Then we want to show that exists some prime number p.
Okay.
Such that p divide n.
Okay.
And this is not very obvious to write, right?
Yeah.
You sort of have to figure out the existence. I mean, it's not obvious how this thing would work. So we're gonna apply the well ordering in order to do that.
Okay.
So maybe I can just write down the definition of a prime number just to be sure we're on the same.
Yeah. In case we have any new people that want to get into math but don't know how to get started.
So definition, a number. So a natural number p, which is greater or equal to 2, is called prime. If its only divisor are 1 and itself. So, for example, two is prime. Why is 2 prime? Because I mean, if it has other divisor, they would have to be smaller than 2, right?
Right.
So there is only 1 and 0, but 1 is one of the one we permit. So
right, because it's a natural number, so the only way you can have it is either 1 or 0 at that point.
Yeah, that's the only. I mean, all divisor of a number has to be lower or equal to that number. So.
Yeah, and if you're watching this on YouTube, guys, basically 1 is not a prime number because it's considered a unit number, like an actual unit.
Yeah, exactly. Actually, the reason why we don't allow 1 to be a prime number is actually associated to ring theory.
Yeah, because like you can have 1 with practically any number. You can have like 1 times 1, you can have 1 times 2, and practically like every number will practically have 1 in it.
Yeah. Actually, if we have time at the end, maybe we can talk a little bit about modular arithmetic. I don't know if you heard of that.
I've heard of modular arithmetic.
Okay. So this is basically the arithmetic on the clock, right?
Yeah. I've heard that analogy.
Yeah. And pretty much if we would allow 1 to be a prime number, we will get something weird in those kind of arithmetic.
I mean, if we have time, you could probably go over a little bit of it.
Yeah. But maybe this will take a little bit of time to prove.
Yeah.
Okay, so we have to first establish this theorem. Okay, so let's prove the lemma.
Okay.
So here's how the proof would work. So we want to use the well ordering property. So we have to build some set which is useful for us. Okay.
Okay.
So let's build this set. Let S to be the set of D, which would be a divisor. Such that D is greater or equal to 2, because we don't want 1 to be part of that set. And D divide our natural number.
Okay.
Okay.
So n is supposed to be the element of natural numbers, correct?
Yeah. So this is the n in the proposition. So
Okay.
n is just some natural number while n is greater than 2 and n is a natural number.
Okay.
Okay. And now we want to apply the principle of well of the ring.
All right.
So there's like one very important condition we should be careful about this is to show that S is actually non-empty.
Okay.
So can you think of a reason why S wouldn't be empty?
Why it wouldn't be empty? Is that your question?
Yeah.
Well, I mean, if we have D as a divisor and D greater than 2 or equal to 2, then practically there would have to be like at least one element in there if we have a divisor and it's multiple in there.
Yeah, so what would be an example of a divisor of n which is greater than 2? Greater or equal to 2?
A divisor of n that's greater than 2?
Yeah.
So, but D can be any number, right? Like any natural number?
Yeah, that satisfies the following that I wrote on the right.
Mm-hmm.
So D has to satisfy those properties.
Okay.
For example, D cannot be 1, right?
Right. So,
because otherwise it will not.
I mean, if you had like if D was like equal to 2 and then basically you had n is equal to 4, then practically like 2 would basically be a divisor to 4, which means that there's literally an element in there.
Yeah, but this is like here you assume that n is an even number, right?
It's just basically I guess like a physical example, like not a physical but a visual example.
Yeah. Okay,
to show that it's not empty based on what I'm trying to.
Yeah. That's a good idea, but I mean, even in your example, you didn't pick the most obvious one, right?
So if you had like D equal to 2, and then let's say the natural number is also 2, right?
Yeah, that's an obvious one. But let's say you have n is equal to 4. What is an obvious divisor of 4?
An obvious divisor to 4, which is 2.
Okay, but even more obvious than that.
4?
Okay, maybe 4. And if I ask you, can you find me a divisor of 9? What would you tell me?
So a divisor of 9, basically.
Like the most obvious one.
Would be 9.
9. So if I give you a general n, what would be an obvious divisor of that?
Practically n.
N. So yeah, you're right. So S is not empty because n is part of S, right?
Right.
Because we assume that n was bigger or equal to 2, and we, obviously n divide n, so S is not empty. Is that right for you?
Let's see. So S is not empty because n is an element of S. Yeah, that sounds like it makes sense. Because if D is equal to n, then practically you would have at least one element in there.
Yeah.
So that actually shows like the set is not empty.
Yeah. And do you agree here that this set is a subset of the natural number?
Mm-hmm. So is there more than one way to prove that a set is not empty? Or is this like the only way to actually show that a set is not empty?
Well, showing that a set is not empty can be a hard thing,
Okay, so it's multiple ways to show that it's not empty.
Yeah.
But in this case, this example is basically what we're going to use.
Yeah.
Okay, all right.
Like for example, if I ask you the following question, let's maybe call it T. Let Z be some, I don't remember what's the definition of that, so let it be just complex number. I think it's maybe not defined at some point, but we will not worry too much about it. Okay, now I have to Z is a non-trivial zero of the zeta function.
Like, are you writing anywhere on the board?
Yeah, on the right.
Oh, here we go.
Such that real part of Z is different from a half.
There we go.
Okay. So, do you know about the... This is not a very good writing, so this is zeta function. So what I wrote here is T is the set of complex number, where Z is a non-trivial zero of the zeta function whose real part is different from a half.
Okay.
So if you show that this set is empty, this is equivalent to have solved the Riemann hypothesis.
Okay, so wait. So is this what the Riemann hypothesis is basically trying to like if you prove this, then basically you've proven that the Riemann hypothesis, correct? Is that what you said?
Yeah. So pretty much any problem in math can be formulated into a problem about is this set empty or not.
Oh, okay.
So here I just give an example, like, this set, if it's empty, then you know that the Riemann hypothesis is...
So, yeah, because I never really understood what the question of the Riemann hypothesis was. I was like, okay, I know it's a millennium problem, but I never understood what the question was asking. Like, I always thought that it had to do with, like, the half line, and I thought you had to, like, prove that the primes, like, lived within that line, but I never really understood what the question was actually physically asking. Or at least, like, what you had to prove in that. But I think with your example, it kind of makes it a little bit easier to comprehend what it was asking. So basically, you're trying to prove that the set, like, other than a half, is practically, like, not empty.
So the zeta function is a function of complex number, and it can have zero.
Yeah.
Like like a polynomial.
Yeah.
And the Riemann hypothesis is about to say that every non-trivial zero, so there's like a family of zero of the zeta function which are considered trivial, which is, they have a definition for that, but we will not bother too much about them.
Yeah.
Basically, all except of those zero will lie on some critical lines, which real part is equal to 1/2.
Right.
So yeah.
Okay.
So you ask if how do we prove that a set is empty or not? Sometimes it can be literally very hard, like this one. We don't think we can do it. I think we can do that today.
Yeah. I'll leave you to do that. You can get the $1 million. Okay, so getting back to what we were talking about. So how is this supposed to help us with the fundamental theorem of arithmetic?
So here we have just showed that we have the hypothesis to use the well order, right? So apply the well order theorem, or just the well ordering of n. S admit a minimum. Okay.
S admits a minimum. So S has to have a minimum within its set.
Yeah.
Okay.
Yeah, because we have just shown that this is a subset of a natural number. It's not empty. So the well ordering said, well, it has to be a minimum.
Okay.
And I will use some notation where it will be very, very obvious what we're gonna do after that. So let's put P to be the minimum of S.
All right.
And now, I use the letter P. So, when you use P in arithmetic, it usually means one thing. This is P is a prime number.
Okay.
So what I want to show, I claim that P is prime.
All right.
Okay.
So P is a prime number. That's
what I'm claiming. So now we have to show the claim.
Okay.
Here is probably easier to use the the minimum assumption. Okay, so we know that p is the smallest number that divide Rn.
Mm-hmm.
So I would just maybe write it down. So p is the smallest
in the set S.
Yeah. No, not just in the set S. Among every natural number, which is not 1.
Oh, okay.
Smallest number, such that p is not equal to 1, such that p divide n. Do you agree with that?
Okay, so p is the smaller number, the smallest number when p is not equal to 1. P is a divisor to n.
Because if you had like a smaller one than p, then it will be on the set S, right?
Yeah, because like I think before you wrote that n has to be greater than or equal to 2. Right?
Yeah.
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 Okay.
I mean, n could be the minimum. In that case, that would just mean that n was already a prime number.
Mm-hmm. But n is the number that has to be the multiple of p in this case.
Yeah. Yeah.
Okay.
So I claim that p is a prime number.
All right.
So what we're gonna do is we're gonna, for sake of contradiction, we're gonna assume the opposite.
Okay. So this is proof by contradiction?
Yeah.
Okay.
Contradiction.
So if you guys are not familiar with the proof by contradiction, is that you're given a proof that, you're given a statement that basically says something and you're trying to prove the opposite. But in doing so, when you try to prove the opposite, you end up proving the actual statement because it turns out to be a contradiction of itself.
So we're gonna assume otherwise. So let's assume that p is actually a product of two numbers.
Right.
Where, of course, a and b are natural number, and a is not 1, and b is not 1 as well. Okay.
All right.
So what can you say about a and b in terms of their size?
Well, obviously they're not equal to 1 and they're like natural numbers, so that means they're not bounded to 1, so they have to be like higher than 1 in this case.
Yeah, so you're right. So a and b has to be, they have to be strictly bigger than 1, so they are strictly bigger or equal to 2.
2, right.
And what can you say about their upper bound? So they divide bound? Yeah.
Were you going to say something more after that?
I can let you think a little bit.
Okay, so you're asking me what do I think, what would I have to say about its upper bound, right?
Yeah.
So basically, if it's the natural numbers, practically it will just go to the infinity within the natural numbers. I know infinity is a concept, not a number, but at the same time it's like, I guess like, if you want to put like, I guess a quote-unquote number, I would have to say a variable like n. It would have to go all the way up to n at that point.
Okay, so here maybe I can help you. So you will be right if a, b were just like, some random natural number, right?
Right.
But here we have some hypothesis. We have assumed that p is a product of a and b, so a and b must divide p, right?
Oh, because like a and b are supposed to be equated to the prime number in question that we're talking about here, right?
Yeah, so we don't know yet that p is a prime, but we know that we are arguing that p is a prime, but we're doing by contradiction, so we assume that p is not prime.
We're proving that basically like p is like a multiple of two numbers that are not equivalent to 1 in this case. They're
not 1, yeah.
Yeah.
So this is the negation of assuming that p is prime, is that p can be written as a product of
two numbers,
right, which are not the trivial one.
Okay.
But let's think a little bit about it.
All right.
Let's take, for example, the divisor of 9.
Okay.
So what are they?
So the obvious one, like we said before, was 9 along with 3. Like, those are the only two that I can think of that are just like obvious to like what we're used to from like regular primary school.
Yeah. So probably if you want to enumerate the list entirely, it would be 1, 3, 6, 9.
So in this case, since B and A cannot be equal to 1, we cannot just be like cheeky and say like, oh, A is equal to P and P is equal to 1 or vice versa.
But
so,
what did you notice in the list? Like 1, 3, 6, 9. All those numbers are smaller than the 9, right?
Yeah, and they're not 1. So
yeah, I mean the 1 is obviously 1, but
yeah.
So do you agree that A and B has to be smaller than P?
Yeah, I think so. Yeah, either smaller or equal to it.
Yeah. But actually, if for example, let's just assume without loss of generality that A is equal to P, okay?
Okay.
Then what does it mean? It means that B has to be 1, right?
Right, yeah, and it can't be in this case.
That can be, exactly. So actually we can assume that the inequality is stricter.
Okay.
Right? Because if we have equality, then A or B has to be equal to P and the other one has to be 1. So
right.
We must have strict inequality.
Okay.
And now the question I want to ask,
yeah,
does A divide N?
Okay, so does A divide by N? Well, let's see here. So A is, so if we think of P is equal to A times B, and we would say that P is a multiple of A. So in this case, if it's P as a divisor to N, then we would have to assume, based on that definition, that A would have to be able to be a divisor to N.
Exactly. So we use the transitive property. So here we have that A divide P and P divides N by hypothesis. By construction, I should say. Then we have that A must divide N as well.
Right.
So do you agree that we have, in that case, as we, so what we have so far is that we have A is greater or equal to 2, strictly smaller to P, and A divide N.
Okay.
Okay, now we're looking for a contradiction.
Okay.
So what was so special about P? Maybe we can just go back a little bit.
Let's see here. Okay, so the proof starts at the proof of lambda, right?
Yeah.
So what is special about P, right? Is that what you're asking?
Yeah.
Okay, so, well, we know that P is supposed to represent a prime number and it's supposed to be greater than 2.
Well, we don't know yet it's the prime number, right? That's what we're trying to prove. But what can you say about the construction of P?
But P is supposed to be greater than 2 or equal to 2, correct?
Yeah, but there's another part which is very important about
P is the minimum of S.
Exactly. And this
so basically A is less than P.
Exactly. But here we have a prime because A, if we look at this, what we hold that, this implies that A is inside of S, right?
Right.
But A is smaller than P. And P is the minimum. Thus, we have a contradiction, right?
Because, like, I'm trying to see... Like, I understand where the contradiction lies. It's just that now I feel like I'm missing a piece. Where it's like... So, how do we know that A is an element of S? I think that's the one place.
Because the thing I wrote here. I mean, we don't need this part, we just need the...
Okay, part. So now I'm trying to look for the place where we said it's a... So P is a minimum of S. Within the...
We can look at the... Yeah.
Okay. So, I forgot what categorized D again. Like D was just a natural number, right?
Yeah, so D is just a natural number, yeah.
Okay.
Which has the following properties. That
Okay,
it's
okay.
greater than or equal to 2 and it divides n.
Okay, so... Alright, yeah, but P is supposed to be the minimum, so basically we have A, which is also part of S, which makes the contradiction that P is the minimum, but also there's a number in there, A, which is less than P.
Yeah.
Okay.
Thus we have the contradiction.
Oh, okay.
So usually when you do a contradiction...
I think like what I got lost at was like when B and A appeared, I think that was when I was like, oh wait, when did we actually consider it part of the set? And I think that's when I was like, okay, like I know the contradiction is there, it's just that I didn't find where A became part of the set, because we already established that P is supposed to be the minimum of the set.
Yeah.
Because I knew A was part of the natural numbers. It's just that I didn't see the part where A is related to S.
Mm-hmm. I mean, the part where we related that to S is when I ask you, is A divide N? And then you said, oh yeah, because of transitivity. And then we said, okay, but in that case...
So wait, so in this section where you just like basically put the parentheses on, right?
Yeah.
Does that basically give us the, I guess, the information that A is actually part of S in that case?
Yeah, I mean, it's part of the information because
it's actually a multiple of P, right? Like supposedly in this proof by contradiction, right?
It's a divisor of, yeah.
So we assume that basically A has to be part of the set because it's part of P, right? Is that the logic, or am I missing something?
So maybe we can just go back here. So what we did is we assumed by contradiction. So we say for the sake of contradiction, we're gonna assume otherwise. Okay.
Yeah.
So what is mean to be not to be prime? It means that it can be written as product of two natural numbers,
right,
which are not one.
Mm-hmm.
And then from that, we establish this bound.
Mm-hmm.
So A and B has to be greater or equal to 2 and smaller than P.
Okay.
And then I ask you, does A divide N? And you say, well, A divide P and P divide N, so A has to divide N as well.
Right.
So we use this property and then we conclude that A divide N. Mm-hmm. But after that, we're clear because we have shown that A is greater or equal to 2, and we also show that A divide N. So this is exactly what it means for a number to be inside of S.
Oh, okay. So it is basically because A is a multiple of also N, right? Because P is a multiple of N.
Yeah, exactly. So
because it was involved with the set we established here, which is D divided by D is like greater than or equal to 2, and D divides into N.
Yeah.
Right? From that set. Oh, okay. Now I get it.
Okay. So this set, I mean, we have some complicated definition, but in your head it should be something like the picture.
Yeah, I think it was just connecting I think it was just connecting it all, because if it was all in front of me, like then I probably would have like made the connection a little bit like later.
So maybe I can just restate the argument. So what we did is we consider a set S, and this S, if I had to put word to define it, I would say, well, it's the set of non-trivial divisor of N. Mm-hmm. When I say non-trivial, I just mean we don't have one in that set, okay?
Mm-hmm.
And I say, okay, then by the well-ordering principle, we know there is some minimum of this set, so let's call it P, and now I claim that P is prime.
So I think I'm gonna ask this because I think it probably best simplifies like what I'm trying to understand here, is that what this set is entailing is that D is not really the main important thing in this set. It's mainly that it's related to N. That's why D is considered like, I guess, the important factor in it. But it's mainly N that's sort of acting as sort of like, I guess, the umbrella idea of S. Is that correct?
Yeah. Oh. So the S, as I said, if I had to wrote the definition in English, I said this is the set of divisor of n, that are not 1.
Alright, yeah, so basically n is acting as sort of like the main umbrella of the whole set.
Yeah. That's like the thing we carry, right? We care about the divisor.
So that's why basically A is in the set, because it is a multiple of like P, which is also a multiple of n. But that contradicts the fact that P is supposed to be the minimum of the set.
Yeah, exactly.
Okay.
So we contradict the minimality of P. That's why we got in trouble.
Oh, okay.
So P has to be a prime number.
So we just basically proved that P is a prime number.
Yeah.
Okay.
And because P is part of S,
yes.
And by definition the element of S has to divide the n's, we have that P divide n. And we won.
Okay.
In fact, this P will be the smallest prime number that divides n, but we don't really care about that.
Oh, okay. So this contradiction basically establishes that P is prime, but it also has to be a minimum in which it can divide into n. Correct?
Yeah, I mean, at the end, once we establish that P is prime, we just have to state that P is divide n, and we're done.
Is n like any natural number in this case?
Any natural number that is greater than 2. So n is fixed at the start, right?
Oh, okay. So is this the actual theorem of arithmetic, or is this like just part of it?
This is like a small lemma.
Oh, okay. So we haven't gotten to the full theorem yet.
No, but now we're close to prove existence of prime decomposition. So now we're gonna prove the existence part. So maybe here, instead of call it lemma, maybe we can call it theorem, or maybe something more ambitious. But so we're gonna call it existence of prime factorization.
Okay. Hey, Mean Machine Rex, how's it going?
So as usual, let's n be a natural number which is bigger or equal to 2. Then what we claim is that n can be factored as a product of primes.
Okay.
Where P1 to Pk are primes. Actually, I can probably just write it as that.
It's Sascha, Mean Machine Rex.
Not necessary.
We're basically learning the fundamental theorem of arithmetic right now.
Not necessary. What's the word in English?
Let's see.
Not disjoint, but they might be the same, but not necessarily different.
Let's see, the theorem of existence of pure factorization. Okay.
Of prime factorization.
Oh, prime factorization, okay.
So this is pretty close to the actual theorem of the fundamental theorem of arithmetic. The only part missing is the uniqueness, right? We just know that at least some prime factorization exists, but we don't know much about the uniqueness part. And now we're gonna prove that using the idea of well of the ring.
Using the lemma?
Yeah, we're gonna use the lemma also.
Okay.
Okay. Here maybe I can. Okay, what is hard about the proof of that is to set. You see, if we go back to the last lemma we proved, what was a little bit hard in that proof was to know which set to fix, right?
Right. Yeah.
So it's not obvious at first. So maybe I can give you a hint about what the good set will be. It's a little bit weird. So maybe I can. Okay, maybe I will give you that, and then we're gonna analyze how we can apply the same idea we did before.
Okay.
So let me this time pose the set S to be the set of n, such that n is greater than 2 and then n also a natural number.
Okay.
such that okay, maybe I'm not writing the proof right, so let me just I'm missing
Is this the same S that you got from the lemma, or is it a totally different S?
It's a new S.
Oh, it's a new S? Okay.
Yeah. So maybe I can call it T, but anyway, I didn't write. So we're gonna assume, so for sake of contradiction, we're gonna assume it's not true.
For the sake of contradiction,
I assume the theorem is false. And now we want to establish a contradiction. So here we can have to do some mental gymnastic about what it means to the theorem to be false here.
Okay.
So have you some experience about negation of a logical statement, or?
Only like I think like the truth tables.
Okay. This one is not probably this one is probably not the most obvious one. So maybe we can just have a talk and see what would be some reasonable things to say. So what does the theorem say? It says, okay, if you have a natural number which is greater or equal to 2, then it has a prime factorization.
Mm-hmm.
So how would you give me a counterexample of the theorem? So what would you have to do in order to do that?
Well, if the theorem basically says any natural number that is equal to or greater than 2, then you have to prove that basically there is a multiple in which it's because you can still break numbers down to their primes, but you have to prove that it's not prime.
So basically the prime is okay. If you have that all natural numbers are written as product of prime, you don't have to show you're good. That's what the theorem says, right? So somehow, if you want to disprove this theorem, you have to find me a natural number that cannot be written as product of primes.
Right.
Does it make sense in your mind, or is that a little bit?
I mean, like, I feel like I have an idea where this is leading to, but I don't know if it's right. Because I remember, like, looking at the theorem before, and I think, like, the way you prove it is that you have a natural number in which you can divide primes from. So in other words,
yeah, but I don't mean about how the proof would work, but I just want to, like, about the logic of it. Like, the negation of the theorem is to say there exists some natural number that cannot be written as product of primes.
Yeah, I think like before when we did the lambda, you would have to have a number where it's like a and b, which is not equal to 1, or like I guess n in this case.
Yeah. So I mean, if we take like some statement that would be something like that, but logically different, it would be something like, I claim that all balloons are blue, right?
Yeah.
And how would you like give me a counterexample to that thing?
Yeah. So the only counterexample I can think of is like you have to actually show that there's a natural number that could be broken down, but it cannot be broken down with primes.
Yeah. I mean, it doesn't have. We just have to show that it cannot be written as product of primes.
Yeah.
Like if we go to the example I was giving about balloon, like if you want to convince me that what I say is nonsense, you just show me a red balloon and you destroy my heart.
Yeah, so I think like you would have to have n, and then it would have to be like there would have to be a divisor within n that is not prime in that case.
Yeah, and it's not possible to break down this divisor into primes. That would be what...
Yeah, that's the only thing I can think of, but I don't know how you would formulate or like write that as like within a proof, like the scratch work behind that.
Okay, so let me... I think you got the idea, so maybe I can just write it down a little bit more. So for the sake of conversion, I assume the theorem is false.
Alright.
So there is a natural number
that is not prime.
That cannot be written as a product of primes. Here maybe I should put primes with the s into parentheses. Yeah, because if the n is already primes, the factorization would just be I don't know, if n is equal to 2, the prime factorization would just be a p1 equal to 2 and no other primes.
Right, and it's supposed to be a product, so it could be more than like 2 numbers.
But it can be just one number.
Oh yeah, that's also true.
Yeah. For example, if the number is already prime, the prime factorization, it will just be one number. Okay. Now what we're gonna do is we're gonna put some weird set. So let me call it T maybe. T will be defined as the set of natural numbers. Of course, we want n to be greater or equal to 2. And now we're gonna ask a weird thing. We're gonna ask that the theorem is false on n. In other words, okay, maybe we can say n cannot be written as a product of prime.
Okay.
Okay.
All right.
And now we're gonna try to apply the principle of well of the ring to this set.
Okay, well ordering of natural numbers, right?
Yeah.
Okay.
So we have to do a couple of checks. First, we have to make sure that this set is actually a subset of the natural number.
Okay.
Is that obvious in that case?
Restate your question again.
So we have to show that T is a subset of the natural number.
Okay.
Is that obvious in that case?
Let's see. N is the natural numbers. Yeah, I believe so, because because the natural numbers also includes 1, but we don't have 1 in this case.
Yeah, but I mean, here the element of the set are some natural numbers, so of course they would be.
And it cannot be written as a product of primes, so yeah, I would think we establish it well as a subset of the natural numbers.
Yeah. Okay. So now, so we check. The T is actually contained inside of n. Now the other thing we have to check is T not empty.
Okay. All right. So
here I'll let you think about why this should be the case.
I mean, the way you writ the set, I would have to say it kind of feels like it's kind of obvious that it's not empty.
Why?
Because basically, well, obviously we have n, and it's element of the natural numbers, so we know the natural numbers is not empty. In addition, n has to be like greater than or equal to 2. And they
but we also have another properties.
Yeah, and basically it cannot be written as a product of prime numbers, which means that it could be a product of, say, composite numbers.
So, but the thing is, can you like you say for the last lemma when we prove it, I asked you to give me an explicit example, right? Of divisor that, I mean, whatever what was the last set, but
I think
here I want you to do the same thing. I want you to give me an example of some natural number.
So basically, so if n is not a prime number, or like let's say n basically is a divisor of n itself, basically it has to be there in this case if it's not a prime number.
Okay, so can you give me like an explicit example?
Because you're going back to the example of the divisor, right? My logic is that let's say n is a divisor of there's something that is a divisor of n, right? But we don't know what it is. Basically, we established for the last one that basically if the obvious example is that, like, before we had what was it? I think it was like 9. And then like what's the obvious divisor to 9? It would be 9 itself because obviously they both divide into each other.
But would you say that 9 is part of this set?
Let's see. A product of primes. Unfortunately, no, it would not be part of this. Because because it's a product of primes, which is 3.
Yeah, so it's 3 power 3.
So in this case, oh, that's a really good, interesting question. Because if it's not a product of primes, then how can we establish that it's not empty?
So, okay, here I will just state. So, at the end, we want to show that all natural numbers greater than 2 are can be factored as prime number, right?
Right.
So this set would actually be empty. That will be the contradiction we're looking for, right?
Yeah, it seems like it's going to be empty no matter what, actually.
Yeah. So, but actually, we assume that the theorem is false, right?
Right.
We did for sake of contradiction. So when we did that, we said, okay, what it means for the theorem to be false? Well, there exists some n naughts greater than 2 that cannot be written as product of primes. So what does it mean? It means that n0 is part and not is part of t. Thus, t is not empty.
Okay, so t is basically the n naught basically establishes that it's not empty in this case.
Yeah. That's why I had to rewrite the thing, because otherwise I was going to write t, but t would have been it would be hard to say if it's empty or not, because we didn't assume that we were doing by contradiction. So so the fact that t is not empty comes from the fact that we assume that the theorem is false.
Okay.
Do you see a little bit better now?
Yeah, so basically n naught is in the set, like, I mean, you just basically made a generalized n in, like, the set notation, right?
Yeah.
So basically n naught is supposed to be, like, I guess quote unquote the origin number within this set, and it's supposed to be the only number that cannot be broken down into a product of primes.
Yeah.
Okay. Yeah.
So,
that's what I can see from what you explained.
So from that, I will try to derive. We're gonna try to derive a contradiction.
Okay.
So now that we established that t is a subset of the natural number, and it's not empty, we can apply the well ordering of the natural number.
Okay.
So by well ordering, we have some t must admit some minimum, right? Which we're gonna call m. Yeah. And now we have to think. Okay. So we're looking for a contradiction. Okay. So we have to think about what could go wrong with m.
Let's see. So m is supposed to be the minimum, right?
Yeah.
I think like the one thing. Oh, thank you for the follow, Nico. UA. I think the thing that can go wrong is that if n naught is less than m. That's what I think could go wrong.
Yeah. But the thing is, we don't really know much about n naught, right?
Right.
As far as we can know, I mean, m could be n naught to m could be smaller than n naught.
So basically, right? Just finding any number that's less than m in this case.
Yeah. So I mean, what we should probably write down is the some properties of m, okay? Just to reiterate. So let's maybe do some list. So m is the minimum of t.
Okay.
So what does this mean? That means that okay, maybe I can write that. So M is the minimum of T. M cannot be written as a product of primes.
Okay.
And lastly, which is very important, M is greater or equal to 2, right? Because it's
Right.
part of T.
Yeah.
So with that, we should be able to do something.
Mm-hmm.
And now, okay, maybe that's a bad thing, but we proved a lemma before, right?
Right.
So, I mean, if we prove that lemma, we can probably expect that it was not just for fun, right?
Mm-hmm.
We should maybe try to apply it.
Okay.
Okay.
All right.
So maybe we can try is to apply the previous lemma to M.
Okay. So the lemma we had was let n as an element of the of the natural numbers n is greater than 2. There exists a p prime number such that p is a divisor of n.
Exactly. So do you agree that we can apply the lemma on
Yeah,
M
because it's greater than or equal to 2. So yeah, it should be able to apply that.
Yeah, so let's apply this to this. So do you agree to me that there exists a p which is prime?
Yes.
Such that p divide m.
Okay.
In other words, we have m
is equal to p.
Let's maybe call it x.
X, yeah, and x is the natural number. Yeah.
Yeah.
Okay.
Okay. So now there's a few cases that can happen, okay?
Okay.
That we have to rule out.
All right.
So now we will shift our focus to x, okay?
Okay.
So first question. Can x be 0 or 1?
Well, I don't think it could be 0 because wait, in this case, are we considering 0 part of the natural numbers or no?
Oh yeah, we are.
Oh, we are? Okay, so 0 is part of the natural numbers in this case. Okay. Well, we can't say that x is 0 because then that would make m 0, which makes it less than 2. So 0 can't be 1.
Yeah. So exactly. So I'm just gonna write down what you said. So it cannot be
0 because it will equate to 0 for m, which is not allowed.
M would be equal to 0, which contradicts.
For 1, I don't think it could be 1 because if p is 2, because if m is equal to 2, then that would make p 2, which is a prime. So I don't think it could be 1 either in this case.
Yeah, exactly, because if x was 1, then m would be equal to a prime number, right?
Yeah.
Which would contradict the fact that m is not the product of primes.
Right.
That'd be 1. So maybe I can just label those. So let me call this one first property and this property. Cannot be 1 because otherwise m equal to p, but that contradicts 2. Okay.
Okay.
So what we're left with is that x has to be greater or equal to 2.
Okay.
Okay.
But isn't that I think I know it's proof by contradiction, but isn't that also establishes the contradiction already? Because if x is equal to 2, then that means it's a prime, and it cannot be a product of prime numbers.
Yeah, but what if x is bigger than 2?
Right. Yeah. That's also another thing.
Yeah. So here we have to establish something. So again, we're gonna use pretty much the same idea we used before. X divide m.
Okay.
So what can you say about x?
X divided by m. Is that what you're asking?
Yeah. So we have that x divide m.
Mm-hmm.
So what can you say about the size of x?
The size of x. Well, and p is supposed to be a prime number, correct?
Yeah. So p is at least 2.
Well, then x would have to be greater than 2 because then we would have a product of prime numbers in this case if p is prime.
Yeah, I did that x has to be greater than 2, so maybe I can write that.
Yeah,
but there's something else I want you to realize. About the upper bound.
The upper bound? Let me see. Because if p is a prime number, then the upper bound... Natural numbers. Yeah, go on.
So in the last lemma, we encountered something similar, right? We had some number which was written as product of 2 other number, right?
Right.
So what could we say about the? For example, in the last case, it was p was equal to a times b. What were we able to say about a and b? Mm-hmm. Do you remember?
So m is basically it's supposed to be, let's see, x times. So basically x is a divisor to m, but p is also a divisor to m. Mm-hmm. Let me see. So it involves the divisors. So
yeah.
So basically p is supposed to be one prime number, but when we say a product of prime numbers, it can only be like all of them are prime numbers, correct? Like all the products.
Yeah.
It's like, so we can have one prime number, but then we have to have the other one be like a composite number, correct? Like
yeah.
So if p is a divisor to m, and m is a and x is a divisor to m, then
So let's go back to the example I gave you during the lemma 1. I said, okay, let's think about the divisor of some number, let's say 9. And then you say you enumerate me the divisor of 9, right? You say it's
right,
1, 3,
right.
6, 9.
And m, like in this case, m would be a divisor to itself as well.
Yeah. But what was this? What was the remark I made you about the list you gave me?
Trying to remember, like what was it that you were remarking about? Like what were you
I was talking about their size.
Their size.
Yeah.
The set size or the minimum?
I mean just the value, like 1, 3, 6, 9. How do they compared to 9?
They're less. They're less.
So
basically, So basically, like x and p have to be less than m at this point.
Exactly. So I mean, usually we should have something like that, right?
Right.
X should be less or equal to m, but we actually know that equality cannot hold, right? Because otherwise p would have to be 1, but 1 is not a prime number.
Right.
So this cannot happen. So this inequality is strict. Okay.
Then 2 is less than x, and then x is less than m.
Yeah.
Okay.
I mean, the part that is I mean, this is not very bad if we put equal sign.
Because we can have at least one prime number.
Yeah. We don't have to worry too much, but this would be enough for our purpose. Okay. Now the fun question: is x part of our set T?
Actually, I mean, if it is a multiple of m, technically, well, because m is the minimum of t, it shouldn't be. But since it's a multiple, it's a multiple of m. I mean, it's a divisor to m, so it kind of is. So it's both in it, but yet it's not supposed to. So it
I mean,
it.
you kind of see the contradiction here. But
Yeah.
I mean, the first part I agree, but the second part I'm not completely convinced. But I agree that x cannot be in t because of what you said.
Right.
So x is not part of t because x is smaller than m, and m is the minimum of t. Oh, you did a great job on that one, actually.
I had to backtrack. That's why. I
But
have a good teacher.
you did great. You did great. Okay, so now we just have to understand what it means x not being t. So maybe I can just copy. Can I copy thing on the stuff? I feel
maybe.
maybe I can use the arrow or something. Okay, let me
Yeah.
use the...
Yeah, I think you can do that.
Okay. Oh yeah, it works. Okay.
Okay, there we go. Yeah.
So what it means for x not be inside of t?
For x not to be inside of t.
Yeah. So there's kind of two conditions, right? There's like this condition you see that has to be greater or equal to 2, and we also have this condition.
It cannot be written as a product of prime numbers.
Yeah. So that's like the two conditions we have to be.
But m is also the minimum, so the thing is that I don't know if this is right, but if x is like, we know x is smaller than m, and it's a divisor to m, but yet it's not part of the set here, wouldn't that conclude that x would be a prime number in this case?
No,
right? Okay, yeah.
No. So what you told me before, you said because x is actually smaller than m, and m is the minimum.
Yeah.
X cannot be inside of t because of the minimum properties, right?
Right.
So if x is not part of t, it means that it must fail at one of those two conditions.
Yeah, that's what it feels like.
Must fail one of these conditions. One of those? I don't know.
Well, x cannot be in there because it's not greater. Yeah, it's not greater but it can be equal to 2 though.
Actually, it is greater or equal to 2, right?
Right.
We established that there.
Yeah.
So it must be the second one that must fail, right?
Which it cannot be a product of prime numbers.
Yeah. So if it cannot be a product of prime, I mean, okay, what it fails is it fails to be. Like, it's really hard to say in English, but it fails to be. It fails to be to be a product of prime number. In other words, x can be written as a product of prime number.
Right.
The double negation was a bit hard.
No. It's like it's kind of like a double negative, so it's hard to say.
Yeah. Does x can be written as a product of prime? So maybe let's say x is equal to pi 1 to pi r, where the pk's are primes.
Okay.
Okay, now we're very close. Now we have to find what hurts the hypothesis. What was the contradiction about that?
So let's see. Thus, x can be written as a product of prime numbers. So it fails in that point, in that regard, right? So the thing is that if it does fail, and basically m is a product of p, which is a prime number, and x, then x must be like, and since x fails, and becomes the product of prime numbers, then that means M itself can be broken down into prime numbers.
Exactly, my man. Good job. Exactly. So M was all along was P times X.
Just a bunch of primes, yeah.
Yeah.
Okay.
Which contradicts
the original set in this case.
Which contradicts the fact that M is inside of T. Thus we have a contradiction.
Okay. Interesting.
Those all n greater or equals to 2 are product of primes.
Okay.
Actually, I want you to put the box.
You want me to put
You did a lot of work there.
No, I felt like you did most of the work, my friend. I was just following along the journey.
No, I think you did great, man.
I think it's just like when math is explained this way, it's like I feel like I'm getting there, but at the same time I'm like I don't know, like based on like what you've been asking me and what I've been concluding within this proof, how do you think my logic is based on what you've assessed? Like what I've been like telling you and I guess in responses to your questions actually.
How would I describe that? So what I would say is you kind of think too many steps ahead.
Okay.
So sometimes I would ask you about some implication. I just say, okay, this implication. So if the hypothesis is true, we want to conclude the conclusion or whatever. Mm-hmm. But then you will start thinking about like 5 steps ahead. You know?
Oh,
like
okay.
you don't state the obvious. Like you think too far ahead sometimes.
Oh, okay.
So I would say you have to kind of
slow down.
Yeah, especially when I was watching you doing the problem you were doing on stream. Like sometimes the prime are easy, and what sometimes gets in your ways that you think like too many steps ahead.
Oh, okay.
Like you should have example. You say like I don't know 2 divides x, then you should say okay x is 2 times something, right?
Mm-hmm. I see.
And like you just state the hypothesis, like all the thing you know. Like I mean, if you look at the proof here, we kind of did that, right?
Mm-hmm.
So at some point I said, okay, we have m, which is the minimum of t. What it's mean to be the minimum of t, and then we said, okay, it has it has these 3 properties. Okay.
Okay.
And after that, we said, okay, we do something with it? Okay. And that's pretty much it. So.
Oh, okay. So, like, basically, like, would you suggest just basically just slow down and just take 1 step at a time, right?
Yeah. Like, make sure to state, like, the very obvious, okay?
Okay.
And once you're done with the obvious, now you can think a bit.
Yeah, I think it's like, so when you say obvious, it's just basically, like, you're saying, like, you know, like, what...
Like, just state the definition or something.
Yeah, like, what information is in front of you and just stick with it. Don't, like, expand too much on it, right? Is that what you're saying? Got you. Okay.
Yeah, for example, when we said like, okay, one thing I can think of an example you did is like, when we established that M is not inside of T, you were kind of already concluding that, M has to not be in T, so we must have some kind of issue, and you were kind of worried about it, right?
Uh-huh.
And then I said, well, don't worry too much about it. Just like state what it means for M not be inside of not M. Sorry, I meant X.
Mm-hmm.
What it meant X to be inside of T. And we say, well, if X is not inside of T, we must have it has to be written as product of primes, and then we simply conclude. Like we didn't have to worry too much about that seems like an issue that X is a divisor of M, and also it's not inside of T. You know what I mean?
Mm-hmm, right. I think it's like for me, I have to like navigate it in my head and like basically remember what I know. And sometimes like I know when you explain it, it's like I feel like it feels as if like we haven't met at the right place, and I have to like find a way to reconnect it. So that's like why it takes me so long to like formulate my thoughts, and sometimes like it is in front of me, but I just don't state it because it's like it's not obvious to me yet. I think that's why. Yeah. Because like I felt like you're asking me for something and it's very abstract, and I'm like, okay, like what is it about the idea or the definition that, or the lemma that I'm not formulated well into words? Because we have to restate it in words to get the proper connection, right? Because I know English is not your first language, so
yeah.
Because like the part where you said it must fail for one of the conditions, I was like trying to figure out exactly like where in the proof that we've written indicates that, and like the only thing I can remember was that x is less than m, and m is supposed to be the minimum. So we know that x is not in t, but at the same time I'm trying to think about like if it's not in t, then yeah, like then I have to rethink, oh okay, then it has to violate one of these conditions, because otherwise,
exactly, yeah.
Then why is it that it wouldn't be in here in this case? And then and then I thought about our previous example, which was, I think it was in the lambda, when it was like we said that a is a multiple, is a divisor of n. And then basically I think we established that a is in S, but then that cannot be because p is the minimum. So I was thinking back to that scenario, and I was like, oh wait, is this the same as that? Which was like, x is in the set, but it's still like part of m. Does that make sense?
Yeah, I know what you mean. I mean, yeah.
I think that's the part where I was kind of like, I think I was confusing myself, because for me it's like whenever I do a lot of examples of something and I got used to it, I always think that example is going to work for another scenario when in fact it doesn't. Does that make sense?
Yeah.
Like for me, I guess when I do math problems, it's sort of like it's pattern and repeat, but then like I realize that if there's something different about a problem, that's when I actually don't do well, because it's like, oh, I have to think of an extra step, or I have to think outside the box. That's what I mean. And I think when I get to a new problem, I get really stuck, because I'm like, okay, what am I supposed to do here?
Yeah.
So I mean, yeah, go on.
Yeah, I mean, this proof is not by any means it's not an easy proof. Okay? So what you did was very great.
Oh, thank you.
After that, it's probably also hard for you to like see the proof, because.
Yeah.
And basically, I was like yesterday in the subway, and I was thinking, oh, I want to show the fundamental theorem of arithmetic, so let me think about the proof. And then I scratched a little bit thing on my paper, and I was like, oh.
Yeah, I mean, it's way different than what I've seen in textbooks. Usually, like I mean, like not textbooks, like regular books that try to talk about this in a much more, I guess, like reader-friendly way, where it's like they would take like. I think they would take like a vast amount of primes, and then they would put like a prime plus 1, and then they would show you like dividing all the, like, I guess like a number n by all the primes, and like the way they explain it is like, oh, if n is actually able to become a multiple, if one of these p's, like one of the primes, becomes a multiple of the set n, then that proves that the fundamental theorem of arithmetic shows that it's a product of two primes, or like primes, something like that. I'm not explaining it well, but usually that's what I see it.
Yeah, I mean, before I look at some of the proof that was like on Wikipedia on some, I mean, very easy to access to, and
I mean,
the proof they gave was not exactly the one.
I mean, you did very well explaining it and asking the right questions for me to think about it, because now I feel like I understand a little bit more about what it is to be a divisor and what it is to be a multiple of a number. So yeah, I really appreciate it, actually.
Yeah. So here really the keystone was like, okay, the theorem of arithmetic is a little bit too, I mean, at least, I mean, we're not done with the theorem because we haven't shown the uniqueness, but we've shown at least existence.
Yeah.
But the thing was a bit hard about existence is, okay, I mean, it's kind of too overwhelming, to have the thing written as a product of primes.
Yeah.
So you kind of have to do like a step back and say, okay, can I at least have one prime that divide my number, you see?
Right.
And this is where the lemma come from.
I see. Well, thank you, Sascha, for like showing all of us this beautiful proof, actually. I mean, even though it's not the whole thing, like, because we didn't prove uniqueness, I think it's pretty beautiful, actually.
Yeah, we could do uniqueness another time if you want.
Yeah, we could do that. We could do that for the other time.
I mean, I was kind of thinking about the clever way to get uniqueness, not very like in a very easy way, like we did here for existence. But I haven't found like a good proof of that. The only thing I can think is the classical proof that use Euclid's lemma, which is a bit of a pain to prove, but I guess we can do that.
Yeah. So like actually like the one thing I would like to ask you is like for people to actually get into mathematical proofs but they know nothing about proof techniques or whatever, like would you suggest just taking an intro to proofs and then basically after they've taken that or like done a book on that, like self-study on that, what would you say the next proof course they probably should try once they master things like, you know, direct proof, proof by contradiction, and proof by contrapositive? Like,
so it kind of depends.
Yeah.
Because what is hard for, I mean, it depends. Like, if it's people at college or, you know, undergrad, it's usually way easier for them to get into proof because their teacher is gonna write a ton of proof on the board, so they're gonna, you know, assimilate some of the techniques. And also they have, you know, graded the thing, or they have you know, a TA that will give the solution to the exercise, so, you know, they can ask questions, they can try solve so they have a lot of feedback, right? So it's kind of easy for them because if they're not steering their ship in the right direction, like the TA or the teacher can just correct them. And
what if you're like self-studying proofs?
Yeah, that's the thing I was about to say. For you, it's really harder than like most college student or undergrad student will go through. So it's really a bit harder. So reading a book is a little bit hard because it does not give you a lot of output, right?
Right.
Input, I should say. So basically, when you're not sure, you just go at the back of the book and you read the solution, and you're like, oh, okay, is what I wrote correct? Because, you know, for a proof, maybe there is multiple way of doing the same thing. Maybe the wording or the presentation is not the same thing, but the proof can still be you know, a valid proof.
Yeah, because I know like when you write proofs, it's sort of like your own, because you're like basically being the writer of the proof. So usually for me, I try to look at the structure, and I also look at the way they phrase things. So it's like, oh, okay, so I did say it not in this way, but I said it in a way where it's like it makes sense to me. And, you know, like like obviously that's not a great a great measurement of like saying you're being better at proofs, but at the same time, if it reads like around like 80% of what the proof said compared to like what the answer has said in the book, I would say like, okay, we got close. So, you know. Yeah. As long as I don't use as long as I don't use the wrong terms or something like that.
Yeah, but it's usually a bit hard to tell what is important in the proving the solution, what is not important.
Yeah, so, and we do have like some people on the Discord server who actually are at like your level and like doing research on their own too. So like whenever you guys usually have time, like we could write proofs and you can check it over whenever you see them, whenever you have the time to reply back, you know.
Yeah, but actually, I mean, it can be a little bit hard if you're studying on your own because maybe you don't have always something like me or some maybe.
Yeah, of course, yeah.
So
like,
what I think would be actually something interesting, which I tried with you a few streams back, was playing the natural number game.
Oh right, yeah. That game was actually pretty fun, yeah.
Yeah, because this thing is very good at give you input. I mean, you can write. I mean, it's a little bit hard because you have to get used to the formal language and you get a little bit of.
The one thing I think they would have to add to that is like giving a restart option. So if you like haven't done it for so long, like you can restart it and do it all over again without the answers just there. I think that's the one thing they would have to improve on that one. So if you guys are not familiar with what we were talking about, so. What is it called? Like Lean, right?
Yeah. So it was Lean, the natural number game.
Yeah. So I'll just open another tab to show you guys. So this is what we're talking about. It's Lean. So basically, during stream I actually did the first tutorial, and I would really love to do the first tutorial again because the last parts I was struggling, and I felt like I needed to like learn a lot more before I actually moved on to the next one, which is the World of Addition. So,
but actually, you can open the link in the incognito window and then start the.
Yeah. So maybe we will have to try that the next time. Like, I mean,
Well,
for
so you-
I'll decide, yeah.
Yeah, or you can also just delete the cookie, but
Yeah, I could probably do that too, actually.
yeah, but I
Okay.
think Lean is like can have like some very good feedback for people like who does not have access to a teacher or a TA. Like,
Yeah, because I feel like proof, like when you do mathematical proofs, is like a totally different animal. It's like you're actually delving into math in a way that's like it feels like it's not tied to things like science and stuff, but at the same time, you feel like it can be, as long as you have the definitions and the definitions are concrete enough that you can actually write ideas through them. In some ways. Which
the
I
only
think,
thing.
yeah.
Wait, yeah, go ahead.
No, which is why I would call like my channel Math Spellbook, because we're kind of spelling out truths for you.
Yeah, the only thing I would probably criticize Lean to be is it's very formal. Like, the Lean compiler will yell at you if you don't do something right. Like,
right. Well, I think that's how it is with every computer program. Like, with like with online homework. Like, if you don't put the number exactly right, or like the decimal place in the right place or something, it will yell at you and basically say you got the wrong answer, even though you're really, really close to it.
Yeah. I mean, usually in Lean, there's like some proof that we would write, on paper, and everybody would say, "Oh, that's a correct proof." But Lean will say, "No, I'm not convinced. Please write more details." So
Right.
it probably force you to be a little bit more pedantic. But I think for people like you and who don't have access to a teacher, it's a very good
Resource.
tool.
Yeah.
I definitely encourage you about learning about proof. It's very a good thing.
Yeah. Go on.
And maybe I would also advise, if you're doing Lean, because Lean is really like a programming language, you should also try to write the same proof you wrote in Lean in a human legible way.
Like, what do you mean? Like in LaTeX?
Not in LaTeX necessarily, but like on a piece of paper or something. Like you say, okay, I wrote this in Lean. It say, okay, we're gonna do induction.
Oh, like basically pre-write before I put it in the computer. That's what you mean.
Yeah. Or I mean, maybe after, like just to be sure that you're both able to write on the computer, and at the same time you're also able to write in a more natural way.
Oh, okay, I see.
Yeah.
Go on. So basically, the stuff that displays on Lean, like like the proof. I guess the proof like of the mathematical form, right? Not the code. Just write that proof down to basically see how it's structured and everything like that.
Yeah.
Is that what you mean? Gotcha.
Yeah. Actually, there was like a fun post by Terry Tao. I don't know if you know that, guys. Okay.
Yes, I know about Terence Tao. Anyone that loves math knows about Terence Tao.
So he did recently a proof about, I don't remember what the subject is. I mean, he's doing pretty much a lot of things, but I don't remember what the subject was.
Yeah.
But he wanted to experience with Lean. So he wanted to formalize his proof he wrote on a recent paper inside of Lean, so that the computer can check it. And what basically he did is that he wrote the proof like normally, like just as any other proof he would wrote. And then he wrote the proof again, but in a very pedantic way, like with like very obvious step. And then after that, he gave it to after that he was able to write it in Leans and have the full proof verified by Lean. So it was
actually, Sascha, since you mentioned Terence Tao for a second, I don't know if you know about the paper he wrote about it was basically about like infinite series, like about limiters or something like that. I saw this on a video on Numberphile, and they were talking about how Terence Tao was like, he made a paper about like if you remember, let's see, where are you on the board? Because you remember when you use the example n times n plus 1 over a half, that's like the sequence of k. Like this thing. In the video, they basically say that like this is like 1 plus 2 plus 3 plus 4 plus 5, and you can make any number. They say that this sequence has a certain stopping mechanism. Like basically, like, because like the fun example that 1 plus 2 plus 3 plus 4 plus 5 equals minus a 12.
Oh, okay, yeah, you mean that.
Like, but this formulation doesn't kind of get you to there. And I'm wondering like what your thoughts about that is, because like obviously like, you know, if we go higher, it's not going to go to minus a 12, but there's a fun way of actually like getting the result, you know, 1 plus 2 plus 3 plus 4 plus 5 equals minus a 12, but it's not through this method.
So yeah, I mean, usually when we write, okay, I mean,
like this is a little fun. This is like a fun side note for you guys. It's not part of the proof. It's just something that I uncovered.
So I mean, probably what people have seen on the internet is something like that.
Yeah.
And this is actually false. Unless if you use like a very weird way of defining what the series what it means for a series to converge. Okay. There's
right.
like.
Yeah, I've seen videos where they said that this is false. Yeah, I've seen those.
Yeah.
Too.
So this is like. I mean, you kind of have to have a very weird way of defining what it means for a sequence to converge.
Because it's only within the Riemann zeta function that pops
okay.
up, right?
This is where it comes from. So we can define actually a function which we call zeta, if I remember correctly. So its original definition is something like that. K to the minus s.
It's s, right?
Is it s or minus s? I can't remember. I think it's s.
I think it's
might be s.
I think it's minus x, because like once you get to the negative numbers, then you basically have like the sequence like minus a 12, I think.
So yeah, I think you're right actually.
Because it's usually when it's the negative numbers, that's when the minus a 12 thing comes up, I think.
Okay. And okay, if you look for example, s, which is a complex number, which is real part is big enough.
Yeah.
So I don't know what is big enough. Maybe bigger than 1, something. Maybe bigger than 2 if we want to be on the side on the clear. Then we get a nice function, which is differentiable and all the good stuff. Okay.
Right.
But okay, so those kind of functions are called holomorphic function.
What does that mean?
So if you have a function, let's call it f, which is defined on some subset, some open set of the complex number, we say f is holomorphic inside of U. If it's complex differentiable. So
if you're able to like do the derivative of it.
Yeah. So it would be something like that.
Oh, okay.
So you know the usual definition of
Yeah, so like for any of you guys that are watching this on YouTube, basically a derivative is just like the rate of change of something. So
yeah, but there's something very special that happens in the complex number. First of all, this limit is not the usual. I mean, it's kind of you can have more direction, right?
Right.
Because in the real case, you would have only like real dimension, but in that case, you also have the complex direction. And this will put some extraordinary constraint on f. Okay, do you want me to give you an example of what it means for such a function?
Probably not at this time, because we're probably gonna run out of time. Like
maybe I can just state. So you know if you have a differential function, there is nothing that guarantees you that the derivative will be continuous or even differentiable, right?
Right.
For example, you can I don't know, take the absolute value square, and then you will get something that is differentiable, but the second derivative does not exist, or something like that.
Right.
If the function is holomorphic, which means just complex differentiable, all its derivative exists.
So basically everything from like second derivative all the way up to like say like the nth derivative.
They all exist, and even that, it's even better than that. F is actually equal to its Taylor series at every point.
So is that like within like I guess like multiple dimensions of C?
No, just
like,
one. I mean, we have similar thing that happen in higher dimension, but And this is like crazy because in the real case, this does not happen. First of all, not if you're differentiable, it does not imply that you have second derivative or third derivative.
Or like that, like to the n degree of derivatives, right?
And,
okay.
And even if you do have all your derivative, it does not mean that the function is equal to its Taylor series. There's like famous counterexample to that. I mean, they're not obvious, but they are.
Okay.
So what it means is that holomorphic function, or another name we give to them is analytic function, are actually rod of steel. They're like super rigid. They're so rigid, in fact, that if you have some small neighborhood, like some open U, and you see like maybe there is like some extension of your function f, like maybe I don't know, you can make your domain a little bit bigger,
right?
And still have an holomorphic function. Then there is a theorem that said that this extension is unique. There is only one way to extend an holomorphic function. There is no other way. For smooth function, there's like a bunch of crazy way you can continue just a smooth function.
Yeah.
But in the complex case, this cannot happen. If you can extend your function, there is only one way to do that. And it turns out that the Riemann zeta function can be extended to pretty much the whole complex number. In particular, it will also be defined for value like for, what was the value you wanted? -1?
Yeah, -1. Yeah.
Yeah, -1. The zeta function will still so it can be extended to -1. And this is where the famous equation we wrote here.
Yeah, like 1 + 2 + 3 + 4 + 5, like, you know, all the way to infinity, positive infinity equals -12.
Yeah, but this theory has nothing to do with the value of -1. Like it's not. I mean, when you come to the front zeta -1, the function is no longer defined by this.
Right.
Yeah, there's like a new thing that happened. So this is where the thing comes from. I don't know if I give you a satisfactory answer.
It's fine because like you know, like this argument with like, you know, the natural numbers like from 1 to 2 to 3, like all the way up equals like -12. I find it very interesting because like, you know, there's some mathematicians that basically agree with it, and there's some mathematicians that are like, no, that's nonsense, that cannot happen. So, you know, I find it very interesting that you know, you basically clarify for your experience. It's like, no, that can't be, that seems like nonsense. But there are some mathematicians and some scientists that are like, no, that's absurd. Because like, actually, I'm trying to right now. I'm going to find the video that talks about it, because it talks more about Terence Tao's idea, and I thought that this was a pretty interesting video. So like, if you have the time to like watch it, like on your own time, of course, because I know you're busy. I'll just send it to you on Discord so you can check it out, and like, because I don't know exactly the idea that Terence Tao presents in the video, but I think it's a pretty interesting view, and you could probably tell me what you think about it afterwards.
Yeah.
But thank you, Sascha, for teaching us all this and having a little bit of like extra clarity on extra stuff that I probably wouldn't have encountered otherwise if I didn't ask. But is there anything you would like to say to our global audience before we depart for today?
I mean, thank you for watching, and follow Matt Spellbook on Twitch and YouTube.
Thank you very much. So yeah, like, since he said that, I will present first our Discord server. So Sascha is there, as well as like a lot of other awesome mathematicians / researchers there. Like, they sometimes research, I think, like physics and computer science as well, in addition to math. So like, if you want to ask questions about that, or like have some intriguing questions you want to ask about math or physics or anything, and for that matter, you can ask there, and we can get into a conversation. And I promise I'll be more active on the Discord server. You can also sub to my YouTube channel if you basically have like tuned into our streams, whether you be lurking or whether you be just like, basically you just been watching for a while but then you couldn't catch up with the rest of the stream. I will upload the VOD here, including this one, which I think this one would be a very valuable one because Sascha taught us a lot of awesome stuff. But yeah, that's pretty much it for today, guys. Thank you for tuning in with us, and also thank you, Sascha, for like teaching us all of this.
You're welcome.
All right. So I'm going to get off Discord, Sascha.
All right.
And I'll get back to like the main channel. All right. But thank you very much.
See ya.
See ya. Alright, so that will end it for today, guys. And always remember, everyone is precious. You guys are just as precious as everyone else. And I will see you guys tomorrow. In addition, all the links will be in the description down below if you want to check out everything from my Discord to my Twitch channel, including also my YouTube channel. So, yeah. So, take care, guys. Bye-bye.